You're listening to the Bare Metal Cyber Prepcast, created to help you succeed in your educational journey. Learn more at baremetalcyber.com, where additional prepcasts, books, and training materials await. Let's get started. Embeddings are at the heart of how modern artificial intelligence systems represent and process meaning. At their simplest, embeddings are numerical vectors, long lists of numbers, that encode data such as words, sentences, images, or audio clips into a form that models can manipulate mathematically. Each vector exists in a high-dimensional space, often hundreds or thousands of dimensions, where the position and direction capture relationships between items. This approach allows models to treat concepts not as isolated symbols, but as points in a shared geometric landscape. Similar meanings cluster together, while unrelated or opposing concepts are pushed apart. By converting abstract human communication into numerical form, embeddings act as the bridge between natural data and machine computation, giving AI a way to reason about meaning through spatial relationships rather than rules or explicit programming. In the context of language models, embeddings serve as the entry point. Before a transformer processes a sentence, each token, which could be a word, subword, or character, is mapped into its embedding vector. This embedding provides the model with a dense, information-rich representation of the token, encoding both its identity and its relationships with other tokens. Without embeddings, a model would see only arbitrary symbols with no sense of similarity or structure. Embeddings therefore form the foundation of natural language understanding, allowing models to distinguish that dog and cat are more alike than dog and carburetor. This grounding enables attention mechanisms and deeper layers of the network to operate effectively, since the input space already encodes rich semantic information. The dimensionality of embeddings is crucial for capturing nuance. While humans think in 3 dimensions, embeddings often span hundreds or thousands of dimensions, each representing latent features that are not directly interpretable, but collectively allow fine-grained differentiation. Higher dimensionality increases the capacity of the embedding space, enabling subtle distinctions between related words, such as king versus monarch, or between contexts, such as bank meaning financial institution versus riverbank. However, higher dimensions also increase computational and storage requirements, creating a trade-off between expressive power and efficiency. Designing embedding dimensionality is therefore a balancing act. Too few dimensions lead to cramped representations where different concepts collide, while too many create inefficiency and risk overfitting. One of the most important properties of embeddings is semantic similarity. In embedding space, words or concepts with related meanings are positioned close to one another, while unrelated ones are far apart. This clustering is what makes embeddings so powerful. It allows models to generalize by proximity rather than relying on exact matches. For example, if a model has seen doctor and nurse in similar contexts, their embeddings will be close, allowing the system to extend understanding even to new queries involving healthcare professions. Semantic similarity also underpins retrieval systems, where a search for automobile can return documents containing car even without explicit keyword overlap. This ability to capture meaning beyond surface form is a defining advantage of embedding-based systems. The idea of embeddings has historical roots in early word representation methods such as Word2Vec and glove. Word2Vec popularized the notion that words appearing in similar contexts share meaning, famously summarized as, "You shall know a word by the company it keeps." It trained shallow networks to map words into vectors, where semantic relationships emerged naturally. Glove extended this idea by leveraging global co-occurrence statistics across large corpora, producing embeddings that encoded both local and global relationships. These early embeddings were static, meaning each word had a single fixed vector regardless of context. While limited compared to today's methods, they demonstrated the immense value of geometric representation, laying the groundwork for the contextual embeddings of transformer-based systems. Contextual embeddings represent a major leap forward. Unlike static embeddings, which assign the same vector to a word in all contexts, contextual embeddings adapt dynamically based on surrounding text. This means that the word bark in dog barked loudly has a different embedding than bark of the tree. Contextualization resolves ambiguity by situating meaning in its immediate environment, creating richer, more accurate representations. Transformers achieve this by generating embeddings at each layer that incorporate information from other tokens through attention, resulting in vectors that evolve dynamically as context unfolds. Contextual embeddings therefore enable models to capture the fluidity of natural language, where the same word can carry multiple meanings depending on usage. Beyond language, embeddings extend into cross-modal applications, where data from different modalities is mapped into a shared space. For example, CLIP, an influential model from OpenAI, learns to align text and image embeddings so that related text and images lie close together in the joint space. This allows systems to retrieve images based on textual descriptions or generate captions for images without explicit programming. Audio embeddings follow similar principles, enabling systems to connect speech with corresponding transcripts or categorize sounds by similarity. Cross-modal embeddings thus create unified representational spaces where different forms of information can interact seamlessly, enabling multimodal AI that bridges language, vision, and sound. Applications of embeddings in retrieval systems are foundational to modern AI products. Semantic search engines rely on embeddings to go beyond keyword matching, retrieving documents that are conceptually related rather than just textually identical. Recommendation engines use embeddings to represent both users and items, capturing preferences and similarities in a shared vector space. For example, a streaming service might embed movies and users in the same space, recommending films that lie near the user's profile. Embeddings thus power personalization, discovery, and relevance across industries, forming the invisible infrastructure of much of the digital economy. Clustering and categorization are natural byproducts of embedding spaces. By analyzing the geometry of embeddings, unsupervised methods can group related concepts without explicit labels. For instance, words for animals may cluster together, while legal or technical terms form distinct regions. Clustering can also reveal hierarchies, with subclusters corresponding to finer distinctions, such as separating mammals from birds within the animal cluster. These emergent structures provide insight into how models organize knowledge internally and enable applications such as taxonomy generation, anomaly detection, or knowledge discovery. Embeddings therefore serve not only as functional tools for retrieval, but also as analytical tools for exploring data relationships. However, embeddings are not free of pitfalls. One major concern is bias. Because embeddings are trained on real-world data, they inevitably encode and propagate the social and cultural biases present in that data. This means that embeddings may associate certain professions disproportionately with one gender, or link particular demographic groups with negative stereotypes. These biases are subtle but dangerous, as they can influence downstream applications such as hiring tools, search engines, or recommendation systems. Addressing bias in embeddings is an active area of research, requiring both improved data curation and post-processing methods that adjust embedding spaces to mitigate harmful associations. Another challenge is drift over time. Embedding spaces are not static. They can change as models are retrained with new data or adapted for new tasks. This creates difficulties for reproducibility, since the same query might produce different results depending on which version of embeddings is used. Drift also complicates long-term applications such as legal or medical retrieval, where consistency is critical. Embedding management therefore requires careful versioning and monitoring, ensuring that changes are tracked and that downstream systems remain stable even as embeddings evolve. Drift highlights the dynamic nature of embedding spaces and the need for governance frameworks to ensure reliability over time. Evaluating embeddings is complex because they are not directly interpretable. Intrinsic measures, such as cosine similarity between vectors, provide insight into how closely related two items are in the embedding space. Extrinsic evaluations, such as retrieval performance or classification benchmarks, test embeddings indirectly by applying them to real tasks. Both approaches are necessary. Intrinsic measures reveal the geometry of the space, while extrinsic measures demonstrate practical utility. Effective evaluation frameworks combine both perspectives, ensuring embeddings are not only mathematically consistent, but also functionally useful. Embedding use at scale introduces storage and indexing challenges. A single embedding vector may contain hundreds or thousands of dimensions, and large systems generate billions of them. Storing and retrieving these vectors efficiently requires specialized databases known as vector indexes, which use approximate nearest neighbor algorithms to search embedding spaces quickly. Without such infrastructure, the computational cost of comparing every vector to every other would be prohibitive. Embedding storage therefore relies on a marriage of machine learning and database engineering, creating pipelines that can handle vast numbers of high-dimensional vectors in real time. A further pitfall is the temptation to over-interpret embeddings. While embeddings reveal patterns and relationships in data, they are not transparent or human-readable in the way words or images are. The dimensions of an embedding do not correspond to clear concepts like gender or emotion. Instead, they represent complex mixtures of features that emerge statistically during training. Attempting to ascribe human meaningful interpretations to individual dimensions is misleading. Embeddings should be treated as functional tools rather than explanatory artifacts, valuable for their ability to power retrieval and clustering, but limited in their capacity to reveal precise cognitive or semantic truths. Embeddings are therefore only useful when paired with indexing systems that allow them to be searched and compared efficiently. Vector databases, approximate nearest neighbor search algorithms, and optimized indexing methods transform embedding spaces from abstract mathematical objects into practical tools. Without these, embeddings would remain locked in high-dimensional space, theoretically powerful but unusable at scale. This connection between representation and infrastructure sets the stage for understanding how embeddings are deployed in real-world systems, and why indexing methods are the next critical step in the pipeline. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. One of the most accessible ways to begin understanding embeddings is through visualization. Because embeddings typically exist in hundreds or thousands of dimensions, they cannot be seen directly. But dimensionality reduction techniques such as TSNE or UMAP can project them into 2 or 3 dimensions for human inspection. These projections often show clusters of semantically related terms, such as animals grouping together, or technical terms clustering in distinct regions. While the projection is only an approximation, it provides an intuitive window into how embeddings capture meaning. It is like flattening a globe onto a map. Distortions are inevitable, but relationships and proximities become visible in ways that help us reason about the structure. Visualization also plays a diagnostic role, revealing whether embeddings for different categories overlap excessively or form clear separations. For educators, researchers, and practitioners, such visualizations make the abstract idea of embeddings tangible, giving us at least a glimpse of the hidden geometry that underlies modern AI systems. In personalization systems, embeddings are the backbone of how preferences are captured and expressed. Recommendation engines, for instance, represent both users and items, whether movies, books, or songs, as vectors in a shared embedding space. A user's embedding reflects their history of interactions, while items cluster according to their attributes. Recommendations are generated by finding items near the user's vector, ensuring that suggestions align with their tastes, even when explicit overlap is absent. This makes it possible to recommend a film a user has never seen that aligns closely with their previous preferences in style, theme, or genre. The same principle powers personalization across e-commerce, news, and advertising. Embeddings thus serve as compact profiles of both people and products, enabling relevance at scale without relying on rigid categories. This personalization capability is one of the most visible and commercially impactful applications of embedding technology. Embeddings also enable cross-lingual alignment, creating spaces where words and phrases from different languages can be compared directly. In such spaces, the French word chien and the English word dog may lie close together, reflecting their shared meaning despite surface differences. This property allows models to support translation and multilingual applications, even without explicit parallel data for every pair of languages. Cross-lingual embeddings create bridges between linguistic systems, making it possible to build search engines, chatbots, and recommendation systems that work across global markets. They also lower the barrier for speakers of less resourced languages to access AI systems, since embedding alignment allows transfer of knowledge from high-resource to low-resource languages. In this way, embeddings are not just technical artifacts but tools for linguistic inclusivity, expanding access to AI across cultural and linguistic boundaries. Domain-specific embeddings represent another powerful extension. While general-purpose embedding models capture broad semantic relationships, they may not capture the nuance needed for specialized fields such as law, medicine, or finance. Fine-tuning embeddings on domain-specific corpora creates spaces where terms acquire meanings that reflect professional usage. For example, in medical embeddings, lead may cluster with cardiac monitoring rather than with metal materials. In legal embeddings, consideration takes on its contractual meaning rather than casual everyday sense. These domain-specific embeddings improve accuracy in retrieval, classification, and recommendation within specialized fields, making them indispensable for enterprise applications. By tailoring embedding spaces to reflect the subtleties of particular domains, organizations can achieve much higher precision and relevance than with generic embeddings alone. Another significant strength of embeddings is their role in enabling zero-shot and few-shot capabilities. Because embedding spaces capture broad semantic relationships, they allow models to generalize to tasks with little or no labeled data. A model that has never explicitly been trained to classify movie genres, for instance, can still cluster films by similarity in embedding space, enabling genre categorization with minimal supervision. Similarly, few-shot learning becomes possible when embeddings allow the model to infer new categories from only a handful of examples. This capacity is vital for applications where labeled data is scarce, such as emerging languages, niche scientific fields, or rapidly evolving domains like cybersecurity. Embeddings thus act as enablers of generalization, reducing dependence on large annotated datasets and making AI more adaptive to novel tasks. Despite their utility, embeddings carry adversarial risks. Because they function as compact summaries of meaning, embeddings can be manipulated in ways that fool retrieval or classification systems. For example, adversarial examples may be crafted to appear semantically similar in embedding space, even though they are harmful or irrelevant. In recommendation systems, malicious actors might attempt to position their content close to legitimate items in embedding space to increase visibility. These manipulations exploit the fact that embeddings reflect statistical similarity, not human judgment of quality or intent. Protecting embedding systems requires robust adversarial testing, monitoring, and safeguards to prevent manipulation. The risk illustrates that while embeddings are powerful tools, they are also potential attack surfaces that adversaries may exploit, if not carefully secured. Privacy concerns are another pitfall of embeddings. Because embeddings are derived from training data, they may inadvertently encode sensitive information. For example, if embeddings are generated from medical records or financial transactions, vectors could leak patterns that reveal private details about individuals. Even when embeddings are anonymized, their geometry may allow reconstruction of original data or identification of individuals through re-identification attacks. This creates challenges for organizations deploying embedding-based systems, particularly in regulated industries. Careful design, differential privacy methods, and strict governance are required to ensure embeddings do not expose more than intended. As embeddings become pervasive in enterprise and consumer applications, balancing their utility with privacy protection becomes a pressing concern. The open-source ecosystem has played a major role in spreading embedding models to a broad audience. Many high-quality embedding models are freely available, allowing researchers, startups, and hobbyists to build powerful retrieval and personalization systems without training from scratch. Open-source projects also encourage experimentation and innovation, as practitioners can fine-tune existing models for specialized tasks or combine them with novel indexing systems. The availability of open-source embeddings lowers barriers to entry, accelerates research, and ensures transparency in methods. However, it also raises concerns about misuse, since embedding models trained on biased or sensitive data may propagate problems when widely adopted. Open-source distribution of embeddings is therefore a double-edged sword, democratizing technology while also demanding vigilance in how it is curated and applied. Hardware considerations shape how embeddings are generated and stored at scale. Generating embeddings is typically lightweight compared to full model inference, since it often requires only the forward pass through the model's initial layers. However, indexing and searching large collections of embeddings can be resource-intensive, requiring specialized vector databases and high-memory systems. For deployments handling billions of embeddings, hardware design becomes critical. GPUs or custom accelerators may be needed for real-time search, and distributed systems must be carefully engineered to balance speed and storage. Embeddings highlight the interplay between model design and infrastructure, showing that representation and indexing are inseparable in practical deployment. Evaluation of embeddings has evolved into a specialized research field, with benchmarks designed to measure both intrinsic and extrinsic performance. Intrinsic evaluations test properties like semantic similarity using cosine distance, while extrinsic evaluations test embeddings in applied tasks such as classification, retrieval, or question answering. Benchmarks such as the Massive Text Embedding Benchmark (MTEB) provide comprehensive comparisons across dozens of tasks and datasets, enabling fair evaluation of different embedding models. These benchmarks reveal trade-offs, such as models that excel at similarity tasks but struggle with multilingual alignment. Systematic evaluation is essential because embeddings are foundational. Their quality directly impacts downstream performance, making rigorous assessment a prerequisite for trust and adoption. The impact of embedding quality on downstream models is profound. In retrieval-augmented generation, for example, embeddings determine which documents are retrieved to supplement a language model's outputs. If embeddings are imprecise or biased, the wrong documents may be retrieved, degrading the model's accuracy and reliability. Similarly, in recommendation systems, embedding quality directly shapes user experience, determining whether recommendations feel relevant or arbitrary. Embeddings thus act as gatekeepers. Their effectiveness amplifies the performance of downstream systems, while their weaknesses propagate errors. This dependency highlights the importance of treating embedding quality as a core research and engineering concern, not a secondary detail. One of the most famous demonstrations of emergent properties in embeddings is analogical reasoning. Early word embeddings revealed patterns such as king, man plus woman approximately equals queen, where arithmetic operations on vectors captured analogical relationships. While such clean analogies are less pronounced in contextual embeddings, the principle remains. Embedding spaces often encode latent structures that mirror human reasoning. These emergent properties illustrate that embeddings are more than compressed data. They capture relational structures that can be manipulated algebraically. This capacity has fascinated researchers and provided intuitive demonstrations of how meaning becomes geometry, even if the full interpretability of embedding spaces remains elusive. Industrial-scale use of embeddings illustrates their centrality in modern AI. Search engines generate billions of embeddings daily to represent documents, queries, and users. Recommendation platforms embed vast catalogs of items in user profiles to deliver personalization at scale. Enterprise systems embed knowledge bases for retrieval-augmented workflows in domains like law, medicine, and finance. These embeddings are stored in massive vector databases optimized for speed and reliability, forming a hidden infrastructure that powers everyday applications. At this scale, embeddings are not academic abstractions but industrial workhorses, silently shaping the relevance, accuracy, and efficiency of countless digital systems. The future of embedding research points toward dynamic, compressed, and bias-mitigated approaches. Dynamic embeddings may adapt in real time to evolving data streams, ensuring representations remain current rather than drifting. Compression techniques aim to reduce the storage and compute burden of embeddings, enabling even larger-scale deployments without prohibitive costs. Bias mitigation remains a priority, with methods being developed to detect, measure, and correct harmful associations encoded in embeddings. Together, these directions aim to make embeddings not only more efficient, but also more ethical, adaptive, and sustainable. As embeddings continue to underpin modern AI, these refinements will be critical for ensuring their long-term reliability and inclusivity. Looking forward, embeddings naturally lead into the subject of vector indexes, which are the specialized data structures and algorithms that make searching embedding spaces fast and scalable. Without indexing, embeddings would be impractical for real-time applications, as comparing each query against billions of stored vectors would take too long. Vector indexes solve this by organizing embeddings in ways that allow approximate nearest neighbor searches to return results quickly with minimal accuracy loss. They are the engines that transform embedding spaces into usable systems, ensuring that meaning captured in vectors can be accessed at scale. This connection makes embeddings and indexing inseparable, and understanding indexing is the natural next step in exploring how AI systems deliver relevance at industrial scale. In conclusion, embeddings transform meaning into vectors, making it possible for AI systems to process language, images, and audio through geometry rather than symbolic rules. They underpin personalization, retrieval, cross-lingual applications, and multimodal systems, while also raising challenges of bias, adversarial risks, and privacy concerns. Their influence extends from academic research into the industrial infrastructures that power billions of daily queries and recommendations. As embeddings evolve toward greater efficiency, inclusivity, and adaptability, they remain one of the most important innovations in modern AI. They are the quiet engine behind semantic search, recommendation systems, and retrieval-augmented generation, ensuring that machines can navigate meaning with precision and flexibility. Thanks for tuning in to the Bare Metal Cyber Prepcast, your trusted source for cybersecurity news and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.